Hi guys, welcome to this presentation, and in this video I will talk about diagonal matrices and one of their properties. Alright, so let me switch to black color here. Alright, so diagonal matrix. So when I think of diagonal matrix, the first thing that comes to my mind is it has something to do with the diagonal. So let's see what a diagonal matrix actually looks like, and let me label my diagonal matrix as A. It will look something like this. So it's going to be D1, D2, and then D3, and rest of the elements are just 0. So this is what a diagonal matrix looks like, and this is a 3 cross 3 diagonal matrix. And a diagonal matrix is always a square matrix, so it's a subset of square matrices. And one thing you'll discover about diagonal matrices are that all the elements below and above diagonal, I mean the principal diagonal of a matrix, which is a diagonal matrix, are 0. So I use the word principal diagonal. What do I mean by that? Well, this diagonal, which is the left diagonal, also called as the main diagonal, is also known as the principal diagonal. So you should remember all of that synonymous terms. Alright, so all the elements above and below the principal diagonal are 0. So let me show you one more notation for representing a diagonal matrix. And by the way, it can be a 2 cross 2 diagonal matrix, it can be a 4 cross 4 diagonal matrix, and like that. But most of the time we are only going to deal with 3 cross 3 and 2 cross 2 diagonal matrices. So let me show you another notation for representing A. So A can be also written as something like this. So DIAG, which is short for diagonal, and then we simply list all of the elements in the principal diagonal separated by a comma. So this is D2, this is D3. So both of these notations are representing the same matrix, which is A. So now I want to talk about one of the very special properties of a diagonal matrix, and this property says that if I raise the matrix A, which is a diagonal matrix, to some power, let's say n, and n is obviously a positive number, positive integer, so the resultant diagonal matrix is going to look something like this. It's going to be d1 raised to the power n, d2 raised to the power n, and d3 raised to the power n. It's exactly going to be like this. So, and all of the other elements are just 0. So this is true, and what I'll do is I'll prove this, and I'll use proof by induction, which is one of my favorite techniques to prove something in mathematics. And we'll prove this, and then if I have proven this for like any n, it's obviously true for n is equal to 2, n is equal to 3, and like that. So let's prove this. I will be using proof by induction. So in proof by induction, we basically have 3 steps. The first step is also known as the base step, and in base step what we do is we prove the theorem, or what we are going to prove for the base case, which is n is equal to 1 in our case. So let's go back to that. For n is equal to 1, we raise the matrix A to the first power, which is the same as A. So we have already proven this for the base case without doing anything, so it's already done. So the first step is very simple, it's done. The second step is in which we make our assumption. So we make our assumption that it's true for some k. It's true for some k greater than 0. which is obviously positive. So if it's true for k, we can write it like, we can say that a raised to the power k is equal to d1 raised to the power k, d2 raised to the power k, d3 raised to the power k, and all of these are 0, right? Because we made, this is an assumption, we didn't prove anything, we just assume that it's true for some k. And now it's the main step. We have to show that it's also, we have to show that it's true for, it's true for k plus 1. Alright, so how will we do that? So first of all, we know that this is true based on our assumption. Let's actually multiply. I want to post multiply this by a. So on both sides I multiply this by a. And remember, in matrices multiplication, the order matters, so I am post multiplying this. And even if you do like pre-multiplication, you multiply a in front of this, it doesn't matter, you're going to get the same result. So when I do that, let me write my matrix A, d1, d2 and d3, and all of these are 0. If you carry out the multiplication process, you will get d1 raised to the power k plus 1, d2 raised to the power k plus 1, and d3 raised to the power k plus 1, and all of these are just 0. So we just proved that it's true for k plus 1, and we made an assumption that it's true for k. So what that means is that by proof, by induction, we can say that it's true for 1, 2, 3, 4, 5, and basically any positive integer, because it's an induction. We just induce this, it's true. Alright, so now I want to talk about one problem relating to diagonal matrices. So let me first write it down. Omega, so let omega be a cube root of unity. So here's omega, and it's a cube root of unity, cube root of unity. And that's just a fancy way of saying that it satisfies this condition, this equation, x cube minus 1 is equal to 0. So it satisfies this, and we are given with a matrix A, which is a 2 cross 2 matrix. So it looks something like this: omega, omega, and then 0 here and 0 here. So as you can see, it's a 2 cross 2 square matrix, which also happens to be a diagonal matrix, and we have to calculate a raised to the power 70. So as you can probably guess, we are going to make use of what we just proved right now, and it's actually a multiple choice question. So let me list down all the possibilities here. So option A is 0, option B is A, option C is negative A, and option D is none of these. So I'll just write none. So we can say, so I just showed you earlier that it's true for any k, right? In this, I think, yeah, it's true for any n, right? If you have a matrix A, which is a diagonal matrix, and you raise that matrix to the nth power, what you will get as the resultant matrix is this. We just showed that, and we'll make use of that here. So this is going, a raised to the power 70 is going to be equal to that same matrix, except we are raising all the elements in the principal diagonal to that exact same power, which is 70. So we get this, and now we know that omega cube is equal to 1, right? Because it satisfies this condition, and you can input omega here and you will get this, right? So we can somehow write omega raised to the power 70 as some multiple of omega cube, and For that, let's divide 70 by 3. What we'll get is 3 times 2 is equal to 6, and then we have 10, so it's 23. So we can write omega raised to the power 70 as omega cube raised to the power 23 times omega, right? Both of these are exactly the same. And the reason to do this is that we know that omega cube is equal to 1, so we can just simplify this as 1 raised to the power 23 times omega, which is just equal to omega. So what we'll get as the resultant matrix is this. Well, we just got our matrix A back, so the answer for this problem is option B, which is just equal to A. So hopefully that made sense to you, and I encourage you to memorize this result, that when you raise a matrix which is a diagonal matrix to some power n, what you will get is this. So I hope that it made sense to you, and if you have any questions and problems or doubts, just let me know. Thanks for watching this video.